right, so our workshop is presented by the following two individuals. Philip Singer, he is a senior data scientist at H2O.ai. He obtained a PhD in computer science with honors at the Technical University at Graz. He holds the title of Grandmaster on Kaggle and has achieved the highest possible rank on the global competition leaderboard. Philip is passionate about machine learning, deep learning, programming, and many other data science related fields. And then we have, as well, Yauhen Babakin. He's a Kaggle competitions grandmaster with a total of 11 gold medals in classical machine learning, NLP, and computer vision competition. He holds a master's degree in applied data analysis from the Belarusian State University. Yauhen has over 7 years of experience in data science, having worked in banking, gaming, and e-commerce industries. He currently holds, he works as a principal data scientist at H2O.ai, where his focus area is deep learning and computer vision in particular. Yauhen has developed computer vision AutoML functionality for H2O.ai's driverless AI and is one of the core developers of H2O Hydrogen Torch. So, hand it over to you two.
Thank you. Test. I guess this works. Yeah, so welcome everyone to our talk. First of all, this will be a bit of an interactive session, so we would all encourage you to first connect to the Wi-Fi, please. I guess most of you are happy to see the Wi-Fi information somewhere. So this is the Wi-Fi hotspot and the password. So I will give you a couple of seconds to connect to this. And then what we are also aiming for is that we will have Slido. So we will have some interactive questions throughout the presentation. And it would be really great if as many of you as possible can engage with it, because it will help us throughout the talk. Because we will try to take your input into account, whatever we will do throughout the presentation. So yeah, this is the Wi-Fi hotspot. And on the next slide, if this works. Oops. And here is the Slido link. So you just go to slido.com and you enter this hashtag KaggleDays -DL. And in the meantime, I will just mention the title of our presentation is Practical Tips for Deep Learning. So we will focus on computer vision today. And we will try to give a general guideline of how to train state-of-the-art computer vision models in transfer learning, and go step by step through a process of taking a data set, having a task at hand, and training a model. And you can even think of this talk now as a mini championship, mini Kaggle Days competition. So we will have like 1 hour, 1.5 hours, and we will try to train a model together. And in the end, we will also show, or in between also, what our steps have been, and then kind of compare the solution from wisdom of the crowd and whatever we have been doing beforehand. So yeah, I hope many of you are connected at this point. Yeah, and again, practical tips for deep transfer learning. Although Walter already introduced us nicely, here is a quick overview of who we are. Both of us have quite a long history on Kaggle. And actually, CPMP said he dropped overnight a spot, and I did as well. So this second place is not correct any longer. So I am third place. As mentioned, I have been highest rank first. I am mostly interested in any kind of deep learning competition, but also tabular. So I don't have any specific kind of use case I'm always focusing on. My strategy has always been to be as diverse as possible. And this is maybe also a general tip I have for any Kaggler, to not be too restricted in the field you're in the field that you have experience with, but rather really go outside and try new ideas, because there's so much interconnectivity between fields nowadays that there's sometimes something I'm learning in tabular competitions that I can apply in a computer vision competition. And also today, what we really want to show you for those who have no experience in computer vision is that the general process is always the same in machine learning, just the tools are different and the tuning is different. So yeah, that's for my person, Yauhen.
Yes, thanks, everyone. Right, so yeah, Philip did mention that we are working at H2.AI together, and we are working on the same projects mostly. And yeah, I'm also a Kaggle Competitions Grandmaster, and my rank is top 30 right now at the moment. I hope to climb higher, but it is hard. And yeah, today we'll be also showing partly some things that we are doing at H2.AI, and it will be kind of this interactive session as Philip described. So let's get it started.
Yeah, so in deep learning, what we are mostly doing nowadays is when we have a task at hand and we have some small data, some large data, and we want to train a model, is the big benefit nowadays in deep learning is that we can do transfer learning. So transfer learning just means in general that there are models that have been trained on generic data. So for example, ImageNet in computer vision. These are so-called pre-trained models. So these are usually pre-trained by either open source practitioners or even companies. And they are usually trained on large data sets, large resources, and these are pre-trained models. And then in deep learning, the nice thing is that we can take these pre-trained models and fine-tune them on our data. So we already have a good starting point to train our models. You have all the weights of the pre-trained models, and then you just take your data, your task that you have, and try to fine-tune these models. And we will really just talk about this fine-tuning step today, and this is what 99% of the models in deep learning in computer vision and NLP are nowadays, that you take pre-trained models and fine-tune them on your data. And as I said before, we will focus on a rather simple task today, which is image classification. But many of the things that we talk today can be applied to either other computer vision tasks or even other deep learning tasks in NLP, in audio, and so on and so forth. So what will we actually work on? As I said before, we will build a classification computer vision model together. And we really want to also test a little bit this theory of wisdom of the crowd, which says that large number of people, the input of large number of people can oftentimes outperform whatever an individual is doing. And I think this is also a nice analogy to what we are doing on Kaggle. So I always want to encourage people to team up with other people on Kaggle, to engage in the community, and we are meeting here. So we are all trying to make use of the wisdom of the crowd. And in the end, we will try to maybe compare some of the results. And also throughout the process, we will always highlight what we have been doing at this step. Things we assume is that, and this is not an easy task, is that when you're working on a competition, you should have some kind of prepared framework, code base of choice for training deep learning models. So this is really maybe even the largest part of doing well in competitions is that you're starting to build your own framework or make use of different frameworks and your own pipeline to train models. So if you're working on tabular competitions, you know you have some steps of like feature generation, training, Optuna, predicting, submitting, so this whole pipeline. And in deep learning, this is very similar. You need to have some kind of code base for training models, predicting, doing validation, and then also doing test predictions. Also, I will not, or we will not talk about cross-validation. This can be a talk on its own, but in the end, we assume that we already have set up some kind of robust cross-validation setup. In this case, it is just a random k-fold. Also, the metric that we will work on is F1 score, so simple classification metric. And you do not need to code along anything. We will discuss and work together. The data set and task that we are focusing on is to predict e-commerce categories. So this is a subsample that we chose from the so-called products 10K dataset, which is also available on Kaggle. The task is you have images and you need to predict the category of this e-commerce image. So this can be clothing. We will see a few samples. The statistics of this dataset are that we have 2,000 training samples and 1,000 separate test samples that we will only check in the end of this talk. And we have 20 diverse classes, but all of them are uniformly distributed. The median image size of the dataset is around 1,000 height and 800 width. And as said before, we do multi-class predictions with F1 score as metric. Just for the sake of this presentation, we will use a tool that we have been, as Yauhen already mentioned before, have been building in H2O, which is a no-code platform for training deep learning models. And a lot of the GMs you see on Kaggle have been contributing to this application. It is not important to you now, but we will use it throughout the talk in order to train the models and show you the results. But yeah, if you ever want to try it out, we have the URL here. You can also find it on Google. And we support currently really a large range of the classical deep learning use cases from NLP to image, video, and audio. And Yauhen will show you the application and the dataset.
Yes, I will show quick intro to the dataset. So here is this application H2 Hydrogen Torch, and it has the same pipeline as any usual model training technique, pipeline, right? So we need to import the dataset, we need to create an experiment, and then we can deploy their model. And in this particular case, we already imported the dataset for this workshop. And it is a pretty simple dataset, right? So we have 2,000 records in the trained data. And the dataset has only 2 columns. So we have the name of the image and some class. And we have 20 classes. And the images represent their photos taken by the users of their e-commerce products. And the underlying idea of that dataset was to match these photos made by the users with the actual catalog at the e-commerce website. So here are some sample images from this dataset. And we will be using this dataset and Hydrogen Torch to build some models. All right, let me go back to the slides.
Yes, and we will start in a second to start tuning models. And I think in general, to a good process for building any kind of machine learning models, it's not a lot of magic. But there are a few different steps that are necessary. And most of you, I guess, also saw it yesterday in the competition, is that maybe the most complex thing is to get a good baseline. But this is really the most important thing. So this involves already building your whole pipeline, starting from loading the data, training a model, predicting the validation, doing the validation on all folds, training maybe another model, and then predicting on test, and maybe deploying the model or making predictions on Kaggle. And really, I want to encourage everyone, whenever you work on a competition, whenever you work on a data science project, start with just this whole start-to-end process. Because after you have that and you have a good setup, you can iterate. And you saw it, many of you saw it yesterday. You're starting to have your baseline, and then you can try, okay, what happens if I add this feature? What happens if I add this hyperparameter? What happens if I switch from light GBM to XGBoost? And so on and so forth. So this is really then this iterative process. So after you have this baseline, you're really getting into this loop of tuning hyperparameters. And this can be infinite. And at some point, you need to make a decision. This is the model I want to put into production. This is a model I want to put on my Kaggle leaderboard. So this is kind of the deploy endpoint. And we will follow exactly this process now. So we will try to get, in general, the best possible model that we now have in this limited amount of time. And we exactly follow this process. So first, we will try to train a baseline model which should give us a point of reference. And then we will tune hyperparameters in order to improve the model. And in the end, we will hopefully have a decent model that we could be happy with in this limited amount of time. And we compare this end-to-end approach also on the separate holdout test data set with 1,000 samples that we will not look at throughout the training process. So let us get started. So first, as I said, we will try to build a baseline model, so try to get a good baseline model as soon as possible. And this really allows us to iterate and experiment fast. And I think a baseline model is maybe one of the most interesting parts, because most of us have different starting points. Most of you, like in life, we have different kinds of preferences for backbones. We have different kinds of preferences for what default parameter sets we use. So this is something that we will try to figure out what kind of baseline model we can build here. For the preconditions, just for you as a reference point, we will try to train these models in distributed mode on 3 A6000 GPUs. We will do mixed precision training. We will fix the optimizer to ADAM-W. We will set the batch size to 32. We will use cross-entropy loss. And we use a single cycle cosine decay learning rate scheduling, which I will explain on the next slide. So this is in general, when training deep learning models, this is kind of a debate between practitioners. But this is what has worked for us always the best and the most straightforward, is when you're training deep learning models, you have a certain number of epochs you train, and you need to set a learning rate and a batch size. We said now before we fixed the batch size, and the learning rate is best in deep learning. You don't keep a static learning rate, but you need to schedule somehow the learning rate, and usually it's some form of decay. So you're starting out with a value for the learning rate, you train, you decay the learning rate, it goes lower, 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 and at some point you're either ending at 0 learning rate or at some very low point. And there are different strategies of doing this scheduling. And what has always worked best for us is to just use the so-called cause and decay learning rate schedule. So we always use this actually. You start out with, and you can see it on the bottom right, you start out with a certain learning rate, and you just decay this in a single cycle based on the cosine function, and then at some point you end at 0. There are some slight alterations you can do, like having a warm-up and then a decay, but for now, and most of the time, actually just this single decay is enough. And what many people also do in deep learning is to do what is called early stopping. So throughout this process, you're training for certain epochs, and let's say you train for 5 epochs, and after the second epoch, you see on the validation metric, wow, the second epoch is way better than the 5th. And then there is this notion of early stopping and best epoch picking, that you just automatically pick the second epoch. But the problem with that is that you are making another decision on the validation set, and this is even a separate decision per fold. Because it could happen that the first fold is on the second epoch, and the last fold is on the 5th epoch. And you would never tune other hyperparameters differently across different folds, right? So what I would always encourage people to do is to train the models that the last epoch is the best, and you just pick the last checkpoint as the checkpoint for interest. And this usually leads to more robust models, and also the ensembling is sometimes better or at least more stable. And this also gives us another advantage, which we will highlight at the very end of this talk, that you can just take these parameters again and train on the full training data without needing to do any early stopping or epoch picking. So yeah, for the sake of this exercise that we have today, we will always do a cosine decay, and we will just try to tune the number of epochs and learning rate.
All right. Yep. And now we'll try to build your baseline model. So as Philip mentioned, we already have prepared our solution, right? So we spent also an hour like at home trying to build the best model in an hour based on this data set. And now it is your turn. So what we will do is we will run some polls in Slido. So there will be interactive questions that you need to answer. And based on your answers, we will make selections for your baseline model. And the first question is, what backbone family would you choose for the baseline model? And here we have listed some of them. So there are like EfficientNet family, ResNet family, and some transformer-based architectures. So what is your favorite architecture to start with if you're dealing with computer vision problem type? All right, so we see some ResNet fans here.
And yeah, just feel free to vote, even if it's not something you're too familiar with, but you might have heard of some of these terms. So we are just trying to get a general feeling.
And also don't forget to click send in Slido. So once you selected your option, you should click send. Right, we have over 50 votes already. Let's give 5 more seconds. Yeah, but I guess the choice is obvious here. So yeah, so let's then, okay, all right, EfficientNet V2 is growing now. Yeah, all right. Okay, let's get it. It's getting close. Right. Yeah, I guess that's it. Right. So for the baseline model architecture, we'll use ResNet. Let me make a note for it. And let's now go to the second selection. So here you need to select the image size that you would choose for your baseline model. And here we limited the choice to some smaller size images for the faster iterations for the baseline model, because you didn't want to train like for ages from the very start. All right, and here everyone is voting for 224. I guess it is one of the default image sizes for all these ImageNet benchmarks as well. Okay, nice. So again, we have about 60 voters already. So let's stop here, and I will make a note that we'll use 224, but 224 image size. Let's go further. The next setting that you need to choose is what Philip already mentioned, right? You need to select this learning rate. And here we are talking about initial learning rate in the cosine decay scheduler. And we'll be also fixing the batch size to 32. And again, if you're not sure, right? So just try to make a random guess, and let's see what it will bring. All right, we're again getting close to 60, and we are done here. And the learning rate will be 1 to the power minus 3. Okay. One more setting is how long do we want to train the models, right? So here you need to select the number of epochs that you would use for the baseline model. And yeah, like the larger the numbers, the longer the models will be training. Okay, so here it was 5 epochs. And finally, one last setting that we will choose for the baseline model is their augmentations. So it is their transformations we are doing to our images before putting them into our deep learning model. And here we have options either like no augmentations at all for the baseline model, or you can start with some soft augmentations, just horizontal flip, or medium with additional shift scale rotate or cutout, and some harder augmentations if you'd like to start with them. Okay, here it is more uniform now. You have 55 voters, a couple of more. Okay, so yeah, we'll go then with their no augmentations option for this baseline model. And now I will switch back to hydrogen torch, right? And we'll try to train this model live with the parameters you have selected. So let me switch back here. So here we go to our datasets, and we can create a new experiment for this dataset. And we will select the settings that you have just chosen. So for the image width and height, we'll go for 224 by 224. And here we'll be mostly using the square images for this workshop. And it is like the default size that we also have in the tool, so I didn't change it. Then for the augmentations, you selected the option no augmentations. And in this case, for us, it is just custom. So in this case, we are using augmentations library for the augmentations. And by default, like we are just using the usual resize to 224 size. The next setting you selected is a backbone. And here we haven't selected the size of the backbone, right? So we selected only the family, that it will be the ResNet. And of course, you might have multiple options like ResNet 34, 50, 100, 152. And usually for the baseline model for faster experiments, it is better to start with smaller models. So in this case, let's go for ResNet 34 as a baseline model. Then we move further. So as we already mentioned, we have fixed loss function to cross entropy, optimizer to atom W. For the learning rate, you selected 1 to the power minus 3. So it is again correct here, right? 1, 2, 3, yes. Batch size is fixed to 32. And the number of epochs is 5. So basically, you just selected a lot of settings that we have by default in the tool. Yeah, and scalar, as we mentioned, it will be their cosine decay. Yeah, so now let's click Run Experiment. And here, as we already mentioned, we have some like old experiments that we trained at home. And we'll be training new experiments and comparing them afterwards on the holdout test dataset. So let's see. Yeah, so we are seeing that their experiment is now running. And we can click on it and see how it is going on. So here we have some charts. So you see our learning rate scheduler, the train loss, validation loss, the validation F1 metric, and how it changes across the epochs. Here we can also take a look at their data insights, right? So we can see here what augmentations we applied to our images. And in this particular case, we haven't applied any, so it is just like 0 images resized to 224 by 224. And this experiment has already finished, right? So if we go to the list of the experiments, we see this validation metric for this experiment, right? So F1 score is 0.665, which is pretty good for their baseline model. And now I will switch back to the slides and tell you what we have selected for our baseline model. So it is what we did at home, right? And for the image size, we also went to this 224 by 224. And we trained it with the same like five epochs and the same 1 to the power minus 3 learning rates that you selected. A couple of difference is, firstly, we had added some soft augmentations. So like horizontal flip is pretty safe augmentation, and it is usually like pretty safe to start with it, so it doesn't hurt. So probably it is better to start with some smaller augmentations instead of like starting without any augmentations at all. And for the backbone, yeah, like we selected this EfficientNet v2, so it was close to the ResNet today. And from our experience, it is like one of the best like recent architectures that is working across a lot of different like data sets. And we selected here their smallest option, so it was B0. So again, like to start with some simple and fast baseline model. All right, so now you have your baseline model. And as we have seen on this chart, it's time to try to improve it, right? And this process is kind of iterative. So you try some different things. You try to improve the model, see if it improves, and then you can change more things. And in this particular case, we have listed a choice of some options that we will be tuning today. And in the next slides, you'll have a chance to use your slider application to rank these options. So you'll have a chance to rank whatever you would like to prefer to tune first, and what is like from your point of view, what is their most important things that we need to tune after we have the baseline model. And here, like I'll just quickly go through them. So we have backbone family, and it corresponds to this, like, either, like, maybe you would like to now switch from ResNet to FishNet family. Then we have backbone size. It is the size of the model, right? So we started with ResNet 34, but maybe you would like to use more, like, deeper networks and use for, like, go for ResNet 50, for example. Then we have a couple of options for the architecture. It is the pooling and dropout. So the pooling is a global pooling that we are using before our fully connected layers. And dropout is their like probability of the dropout we are using between like our last layer and the fully connected layer with number of classes. Then we have the training parameters that we already discussed, number of epochs and learning rate. Then we have their regular augmentations. So it is this soft, medium, and hard like strategies that we have seen. And also here we have mixed augmentations. And mixed augmentations means their augmentations like cut mix or mix up. It is a type of augmentations where you combine multiple images together. And we will see a couple of examples later. But like for you, it's just like the idea is combining multiple images together in a single image. And finally, you can also tune the image size. So maybe you would like now to try smaller image sizes, or maybe go upper, right, and try larger images. And so here, I will switch to Slider now. And in your application, you should see this ranking list. So you don't have to select all the options there. So you can just select like a couple of options that you'd like to try first, to tune first. And then you could also rank them according to your priorities.
And you don't need to rank the whole list. You can just do 1, 2, 3, and then send.
All right, so we have 26 participants ranking at the moment, 30, nice. You can also edit your choices if you'd like to edit, but do not forget to click send once you're done. All right, we have 45 already. And we see that currently number of epochs and learning rate are winning this race. All right, 2 more people are ranking, 3. All right, so yeah, so I guess here we have like 2 clean winners, right? The number of epochs and learning rate. And what we will do is we will run a grid search over these 2 hyperparameters. So it means that we will try like different combinations of number of epochs and learning rate. And we can afterwards evaluate what was the best combination. So let me start this experiment. So I'll go back to their application. And here you can click like new experiment in the application, and it will start from this experiment with the same settings it had before. So you can check here, right, that we have our like no augmentations option, and we have ResNet 34 as a backbone. And in this particular case, we will enable grid search, as I've mentioned, and we will try different values of their learning rates and epochs. So let's go to the settings. And here we need to select the settings for the learning rate, right? So probably we'll select 2 smaller ones. Maybe even, I think it is enough. Philip, do you want to go lower? For the higher one, okay. Let's try the higher one. Like, let's do it like this. Yeah, so if you have any suggestions, please speak up, right? If you want to try some specific learning rate. But I guess, yeah, we have tried one value like larger than your initial value, and one value that is 3 times lower than the initial baseline model. And then also, let's tune the number of epochs. So yeah, I don't think that there is a point to go lower in the number of epochs for this particular data set. But as long as we have no augmentations, all right, let's maybe try 3. and 7 or 10, maybe 10. All right. So yeah, so now we have like 3 options for the epochs, 3, 5, 10. And we have 3 options for the learning rate. And we'll just like run the full grid search over the settings. So it will be like 9 experiments in total. So you can click run experiment here, and we'll be in our like screen with these 9 experiments. And here you would see your options. So it is like different number of epochs and different number of learning rates. And these experiments will be trained one after another, right? So it will take some time. And in the meantime, we'll switch back to their slides and discuss it.
Yes. Yeah, so actually what we would suggest is actually what all of you chose now, is to exactly tune the learning rate and epochs. So from our experience, this is definitely the most important thing to tune in the beginning. And you can already sometimes get quite good boosts on just tuning the number of epochs and learning rate. And what is important to say is that this is also very specific on backbone and data. So there are some common rules that you learn throughout the time while training models. What kind of learning rates work well for what kind of backbones. So I guess for ResNet-like and EfficientNet-like models, the ranges we chose now already work quite well, what we saw. But for some transformer-based models, so width, SWIN, and so on, you sometimes need to go way lower in terms of learning rate. And there you're converging more similarly to learning rates that you're also seeing in NLP, so in the range of like 1 E-5 and maybe even lower. So this is transformer-based, and they usually need lower learning rates. And learning rate and epochs also gives you a very good feature set for combating overfitting and underfitting. So actually, opposite to what many people think, higher learning rates can actually prevent overfitting because it doesn't make very small, precise steps at some point. And you also see this on Kaggle sometimes, that people even use differential learning rates. So maybe even having different learning rates for the backbone, for the head, or the classifier of the model in order to tune this and balance this out. So you can really go quite far by just tuning these learning rates, maybe even on different parts of the network differently. So yeah, as I said, good starting ranges are usually in this range that we are now in, also for these experiments. Epochs in computer vision usually ranges in something like 2 to 10, but of course this very much depends on the amount of data you have, on the quality of the data, on the types of augmentations and regularizations you're doing. But this is kind of a good starting range we are usually in. And yeah, as I said before, a good strategy, and also what we are doing now, is to keep the batch size static and only change it if necessary. When is it necessary? It is necessary when you're running out of memory. So when you're increasing the model size, when you're increasing the image size, if you're switching backbone family, sometimes you can run out of memory. And if you do that and you're switching, you can just reduce the batch size, and by the same factor, you're reducing the learning rate. So if you have something like, currently your best model has batch size 32 and learning rate 1 E-3, then you would go divide both by half, go to batch size 16 and learning rate 0.005. So this is kind of a good rule of thumb to get started if you need to reduce or even increase the batch size if possible. So yeah, this is kind of what we did in step 1, so very similar to what you are doing now. And Yauhen will switch back to the experiments and we will see what we are getting. So maybe even our baseline settings were already best, but I think there's not much improvement yet, right?
Check it out. We started, let's see when what was the value we started with. So we started with 6675. So we already have some improvements. So let's back to our experiments. So all of them are almost finished. And let's
sort
see.
Maybe.
Yeah, let's see the best ones. All right, so we have 3 epochs and a bit smaller learning rate, and 5 epochs and also a bit smaller learning rate. So it means that, yes, probably a bit smaller learning rate is better for this particular setup. And we can also like compare this experiment with for example, that we had before, right? This 1 to the power minus 3 with 5 epochs. Let's select the best one. So yeah, so it's here you could see that we're using like lower learning rate and we're training for less epochs, and it is starting already with a pretty low validation loss, and F1 metric is also better here. And let's see the difference here. Yeah, so the difference was the number of epochs and the learning rate. Okay, so let's go back to our experiments. We have
So the reference was
068, I guess, but we already have one better one. Let's see. Yes, the reference was 06675. And we already have something even better. Yes, we have 7.4 now, and it was trained for 10 epochs. All right, so again, it is using like smaller learning rate, right? So it looks like, like using smaller rate is better, and even increasing the epochs is also helping. And it is a bit surprising for me because we're not using augmentations. Okay, let's see. Yeah, so we can see, right, the train loss converged to almost zeros from the middle of the training, but the validation loss was still not that bad. Yeah, and we see that right here in the end, our final performance is worse than some checkpoint here in the like 8th epoch, but we are not selecting it. And as Philip described, right, we're always aiming at this last model.
Yeah, but this already shows you nicely what kind of boosts you can get by just tuning exactly this number of epochs and learning rate. So we didn't change anything else, and we already got from something like 066 to 0775. So this on Kaggle leaderboard, this would be already quite a significant boost, I would imagine. So yeah, this is definitely one of the most important things to tune, and we can see it live here.
All right, and now we'll make another iteration of this process, right? So again, you'll have an access to all these options again, and we will start with this best experiments that we have so far with this number of equals and learning rate, and you will have again to rank the options that you would tune next. So you can again maybe you would like to tune learning rate and epochs again, right? Maybe you can try you want to try some other values, or in this case you would like to try some other settings. So let's go back to the slides and go back to another poll. So the idea here is similar, right? So you again need to select a couple of options, rank them, and send it to the results.
Yes, and one thing to note is that we have 2 more. So after this, there's 1 more tuning round, right? So keep that in mind that you only have 1 more chance after this to tune stuff. So pick wisely.
Okay, now number of epochs and learning rate are at the bottom of the list. And on top we have augmentations, dropout, and backbones.
And mix augmentations refers to cut, mix, and mix up, just to be clear.
All right, some people are still ranking. But we can already see, right, that most of you are selecting options related to some regularization technique, right? So you're selecting augmentations or dropout. And I guess at this stage, it is a good choice to try to, kind of add some augmentations, maybe mix augmentations. All right, I guess we're done. 54, so we have like augmentations, mix augmentations, dropout, and backbone family. So how shall we construct? So for sure we will tune the regular augmentations. Maybe we can add, I would probably skip mix augmentations for now and maybe try to combine it with backbone family or backbone size. All right, let's try it now. Yeah, probably only augmentations is the best choice based on the votes, right? So we have regular and mix augmentations. Okay, so we are starting now with these best experiments you had so far. we create a new experiment from it, and now we will tune the augmentations. So I'll again enable the grid search. And in this particular case, we have these predefined strategies for the augmentations, right? So we have this soft, medium, and hard. So I would not go for the option without augmentations at all. So I would at least start with soft augmentations. And maybe we can also select soft and medium. Should be enough, I think. Do you want to go hard?
Hard was quite popular in the first vote, so maybe
all right. Let's have hard. And then we have this mix augmentations here, right? And as you said, it is mix up and cut mix options. And let's just go then for all of them. So we'll have one option disabled without mix augmentations, and then mix up and cut mix.
Maybe we can remove the soft augmentation.
Do you want to start with medium directly?
Yeah, it will be too much.
It is 9 versus 6 experiments.
Okay.
Yeah, let's maybe remove soft. Yeah, I guess medium should be better. So just for the sake of time, to make it faster, because we already have 10 epochs training. So yeah, so we'll have 6 experiments, 2 augmentations that are just based on the individual images, and 3 options for the mix augmentations. So let's start it now.
And maybe one thing to add here is that usually when you're going with like larger augmentations, more mix-up, you would also try to tune the number of epochs at the same time and maybe potentially increase it. But in this case, we are already on 10 epochs, so I think we can just stick to that and just tune the augmentations. And we already saw some overfitting potential in like the later epochs. So it should maybe be helpful or not, we will see.
Yeah, and here for this first experiment, we already see some cut mix augmentations, right? So for example, in this image, you can see that we are mixing 2 images together. So one part of their image is taken from one image, and another is taken from another image. And the label in this case is kind of soft, right? So we have like 50% label for one class and 50% label for another class. And yeah, so let's wait for these experiments to run. And let's go back for the slides for a moment.
Yeah, so our step 2 was also augmentations. So yeah, it perfectly matches what you have been selecting. So augmentations, for those who are not too familiar with it, it's one of the great things from my perspective in computer vision is that you have augmentations. So augmentations are just a way to augment and randomly change your input images. And it is an artificial way of generating more training data and give more diversity to the training data. And there are really a lot of different ways of doing these augmentations in images, which starts with simple things like randomly flipping horizontal or vertically, resizing, randomly resizing, randomly rotating the images, shifting images. Cutout is a very popular technique, and we can see it here on the left-hand side. You just randomly pick certain areas of the image and mask it with like a certain constant value, like black here. This is a natural way of doing basically dropout just on the input image side already. Then what in the last years has heavily popped up is different techniques for mix-up and cut mix. But this is just a general idea of combining 2 or even more multiple images together in a random way. So mix-up would just be a ratio of taking one image and a random other image with a certain ratio. So let's say you pick it with like 60%, you take the pixel values of one image with 40% of the other image. And then there are different techniques of combining the labels. In classification, you usually do a ratio. So you would say then actually 60% of the label is this and 40% of the label is this. Cut mix works similarly, but in this case, you're not overlaying the pixels, but you're overlaying areas of an image. So for example, you take like the left top corner of one image and the rest of the other image, and you're combining it. Both of these techniques have a lot of potential, and there are a lot of problems actually where you cannot even get a good enough score without using them. And it depends on the data if mix-up or cut mix is more helpful. There are definitely use cases where cut mix is performing way better, and others where mix-up. Cut mix has the only issue is that if the label is located in a certain area of the image and you're overlaying it and you don't know where actually the information for the label is, you lose the information. But sometimes the label is more spread out over the image, and this can make more sense. yeah, as I said before, sometimes if you increase the augmentations, which is just another regularization technique, you sometimes need to increase the epochs, need to maybe retune the learning rate, maybe go lower a little bit. And this is really something to tune. And this is what brings me joy the most, actually, in computer vision, because this is really the area where you can bring your own ideas in the most and have the most room for experimenting. And yeah, and now we will switch back to your experiments and see if anything was helpful.
Yeah, let's first start with a reference. So for the first stage, our best experiment achieved 0.7425 F1 score. So it is where we started. And let's see now our augmentation experiments. So 4 of them are already finished, and we have one that is better. Let's see what it is. So yeah, so it is using this medium augmentations and cut mix, and it was the first one that was running there. So it is slightly better than what we had before. And let's wait for one more. Yeah, we have one more left. And in general, I guess, what worked the best? Yeah, so either medium with cut mix or hard and disabled mix augmentations. Yep.
And usually this is also a good time to look into how your predictions are actually doing. So this is usually a good time to start like looking at the validation set and looking what kind of predictions are performing well and not so well. And maybe sometimes this can give you also ideas for augmentations. So here we see like random validation samples, best validation samples, and worst validation samples. And we can sometimes, for example, we can go to worst validation samples here, see like what type of samples we are predicting very badly. And yeah, so I guess with some of them I might have also issues. This should be not too complex, I guess, but this one looks hard. And sometimes this can also give us like ideas for augmentations. If you can see a little bit where your model is doing well and not so well.
Right. And I think we are done with this stage. Let's again, all right, so we have two candidates. They achieved the same scores. In terms of F1 metric, let's compare them maybe to see the training.
Cut mix and not cut mix.
Yeah, so it is cut mix or not cut mix. That was a good guess. So here's the charts, right? So we see that their orange line is probably the option with cut mix, right? So the train loss is much higher now compared to the option without cut mix. But at the same time, validation losses and metrics are kind of similar. So yeah, here probably we need to select one of them to start our last round of tuning. So maybe let's make it interactive with like raising the hands. So who would choose the option with cut mix now? All right, and now there another option. Who would choose the option without cut mix? Yeah, I guess cut mix has won. All right, so we'll go with cut mix for their next stage. And in this stage, it will be their final parameters that we would tune for this problem. And you will not be given a ranking, but you will be given just a single choice question where you would need to select the most important things that you would tune last now to try to improve this model that you've got so far. So let's go again to your Slido. And here you have the same options that you had before, but as I said, you should just select a single option from the list that you would tune last here. All right, we have 40 votes. 10 more. Okay, over 50. it seems that the image size is winning the race, and I guess it is a very good choice for the last tune. Do you have time? Yeah, so it looks like we have time to maybe try two options now, right? So maybe we can go like with image size and backbone size simultaneously, right? So maybe run a small grid and try to increase both of them. And as Philip mentioned, their median size in the data set was 1,000 pixels by 1,000 pixels. And we were training the models only with 224, right? So it seems that there should be some potential in the image size. So let's start again with our best model here. And we need the option with cut mix. All right. So yeah, so Philip is suggesting that we would run one experiment with their image size. So let's tune image size. And let's probably just increase it to 512, I guess. And let's just run a single experiment here. So I think just increasing it to the square 512 should be enough here. So let's run this experiment. And then we will also start again from that best experiment with cut mix. Or we can start from this one. So here, together with the image size, we can tune the backbone. And let's probably stick to this 512 size to use larger images and try to increase the size of the backbone. All right. So we have already trained ResNet 34, so we can train ResNet 50. And maybe we can try SE-ResNext 50. Do you have any other suggestions? So maybe someone wants some other architecture. Yes, something around ResNet. All right. So we can try some other architecture also. So yes, we can just select from this list. So whoever transformer. All right. So we can. Let's maybe try like vision transformer here, right? Yeah. So basically, like here we support the whole list from the team library, right? So basically, you can just select from this TIMM library, right? The whole list of like 800 models or like 700 models. So we support all of them. So yeah, but it is hard to test all of them, right? So here we have some kind of like predefined list of some architectures, but we can also like use any team library. But I guess there were suggestions about transformers, right? So like for this last experiment, I guess we can try some vision transformers, and let's probably go for page 32. All right, Philip is suggesting that probably we'll need a lower learning rate for the transformer-based architectures. So yeah, so let's probably stick to the ResNets. Yes. Yes, this is a good point, right? So someone is suggesting to try a mobile net architecture in case we'd like to obtain smaller model and see what is their degradation in its performance for the smaller model. And it is usually best like choice for their deploying the models. But here we're kind of like playing this game of Kaggle, right? So trying to increase the quality no matter what the size of the model. And that is why. So usually like here in the last stages we're trying to go higher and try like larger architectures. Yeah, so ideally, you should not tune like multiple things simultaneously, right? So we should not like increase their image size simultaneously together with their the backbone size. But in this particular case, we kind of like know that for this particular data set, 512 image size works better. So that is why we're like just saving some time and starting with these sizes. But yeah, but it is a nice point. All right, so let's run just 2 more experiments here. And we also have our experiment finished, I guess, for yes. So here was our experiment with increasing image size. And we can see already that it scored like 7925, right? And it was like our reference was about 7.5, so we've got 7.9 now. And on top of this experiment, we now started 2 more experiments with the same 512 image size, but with their larger backbones. So let's see how they will perform. And in the
and one thing to add now, if you're seeing that, okay, 512 is already giving a huge boost, right? You might even want to try higher, but we will stop at 512 here. And also we didn't try higher, but it would be the logical step, right? You see something higher works better, you might need or want to go higher if it's possible and makes sense for also your production environment.
Absolutely. And now let's go back to the slides, and here we have also our last step.
Yes, so our step 3 was also very similar, to increase now the model and input complexity. This can also mean decreasing sometimes, but basically in this case we have started very low and now we want to increase the model complexity. So in our case this was changing the backbone of the same family. So as we started with EfficientNet v2 P0, it made sense for us to try like P3, maybe P5 and so on and so forth. There's also this very nice EfficientNet v2 models in TIM library with like tiny small medium, which we personally like to use. So we also tuned a few of those variants. And if you're increasing the complexity of the models, they can pick up more fine-grained signal, right? So you also need to reiterate sometimes with previous tuning. So it might even need more augmentations and regularizations. In our case, we already have quite a lot of augmentations. We have medium augmentations and cut mix. And we also might need different learning rates and epochs. It can be the case that larger models need lower learning rates, specifically if you switch between the families, as mentioned before. But in this case, also if you go from like P0 to P5, sometimes you need to decrease the learning rate. And yeah, obviously larger image size, this makes sense, right? You start with something like 2 to 4 in our case, and then you go higher in the end and try to improve. And at some point, if you go higher, you might stick to that larger image size and tune further from there.
All right, and now let's take a look at our 2 final experiments here. So let's again firstly see our reference. So our reference was 7925. And let's see now. So 1 is finished, and it is already 8.3. So it is a very nice score for the data set. And it was as ResNext 50, and we have our ResNet 50 still training. So it is about 40 seconds to finish, and we can compare them in the meantime. All right, and let's see which is which.
Yeah, the one that is training doesn't look better, right?
Yeah, so I think that
not finished yet. So.
Yes, that as ResNext is better here. All right, so now we have our final model here, right? So probably it will be as ResNext. So let's wait for a couple of moments. ResNet 50 finished, right, and it is even worse than ResNet 34. So maybe, as Philip mentioned, it requires some additional retuning now because we have like a different image size. Maybe we need to retune the learning rate and maybe augmentations again. And here what we will do now is we have our final experiment. And as we mentioned in the very beginning, we have a holdout test data set with 1,000 new images that the models haven't seen during the training. So let's just select this experiment, click predict here, and we'll run the inference on this test CSV data set with 1,000 images. So let's run it and see the performance. And here we see their list of predictions that we also pre-run before. And it was our reference that we managed to achieve together with Philip, right? So we started with some baseline models that we mentioned, and it was like 7.8 on this test dataset. And we managed to improve it to 8.5 on this test dataset. So it was our final result. And now let's see what you've got. So yeah, let me click refresh. Yeah, and you've got 0.83. So it means that it was close, but we have won this time.
But But CV and your test score is basically the same, right? That's impressive.
Yes. So on the CV result was really high, right? So here, like on this validation, it was 8.3. So I guess it is similar to what we've got as well.
Yes. And yeah, so now at this step, you would try further from this point, right? So we now improved from within an hour or something, or even less, from 0.66 to 0.83. You can either stay longer if you have longer time in the earlier stages to have faster iteration, right? And only increase like the size and the backbones later on. Or if you have the resources and you feel more comfortable to continue tuning from like always the better areas, you can now start with this 0.83 and tune it further. I think one area to, and I think we have a slide for further tuning, right? So I will talk about this afterwards. When you have now this model for production, for prediction, there are also some kind of inference tricks where you don't need to retrain the data, but you can directly do it in inference, and it doesn't cost you sometimes much time to do these inference tricks. So, okay, the first one is retraining the model, but in the beginning we mentioned that we just did a Cosin decay of the learning rate, and we are always picking the last epoch. So what we can do now, and is what also many of the top Kagglers nowadays do, is that you retrain the best models on the full training data. Specifically in deep learning, this can have some benefits versus averaging multiple folds, and it can be even cheaper to train, because oftentimes you do not even have the resources to always optimize, let's say, 5 folds together, right? So you're sticking to a single fold, and then you need to either retrain on 5 folds and average them, or what you can just do is that you just take the whole training data and train the model on this whole training data with exactly the same settings that you got in your optimization routine. Because we are always picking the last epoch, so we do not need to make any extra choices. And usually the more data, the better. Not always, but most of the time. Blending and ensembling obviously is another big area. So you can either, so this is also one thing I want to note, is that deep learning models are more random than maybe some more classical GBMs. So it oftentimes depends heavily on the seed. I would personally never recommend to fix the seed, but rather investigate what is your variation about multiple reruns of the same model at some point. Specifically on small data in regression-like problems, you often see a lot of variation between seeds. And if you have like a lot of time, a lot of resources, it can be even good to always evaluate only on an average of like multiple runs of the same settings, because this is more stable and tells you way more, or gives you way more confidence that a setting is not lucky now, but it is more robust for multiple reruns. But you can also use this for making predictions in the end, either in your deployed models or in inference on Kaggle. So just different seeds for the same settings. Diversity matters, different backbones, different augmentations, epochs, image size. So whatever we tuned here, I would always encourage you to not throw away any experiments you ran throughout your process of training models, because now at this point we could go ahead, write a simple Jupyter notebook and try to blend different old experiments that we have and just try to find the best combinations out of all the experiments we have on the validation set. And this might even tell us an interesting direction to go for diversity, because maybe cut mix blends very well with models trained without cut mix. I don't know, right? So this is something that at this stage you could also try and then try to build diversity. And test time augmentations is not free, because you need to run the inference 2 times or more times, but you just can randomly, for example, flip the prediction image, make predictions on the normal input, on the flipped input, and average it. So this is called TTA, and this can sometimes even give you an easy way of improving your score. And also, I think it's not mentioned here, but also you can do inference on larger image size than you trained on. This is also another trick that can sometimes help for a few tiny points.
Yeah, and just maybe to make our last interactive round, we'll try to blend our models together, right? So we have our model with 8.5, your model with 8.3. So yeah, we have just created a simple notebook to try to blend them together, right? And let's see what results we can achieve. So here we're just like averaging their probabilities and calculating their F1 score for their argmax for these probabilities. So let's see what we can get. All right, so it is 861. So combining like these two models together, we can get another like digit here, like and get into 861, blending these two models together.
Yeah, so just by blending now your model with ours, we got another nice boost. And this is really a diverse model because it's a different backbone family. It's with cut mix, we didn't use cut mix, and yeah, so that works usually nicely. I think there was also, okay, so there are some questions here already, but we also I think there was a question with like vision transformers, right? And do we still have the results to show? I think we also trained some, right?
Yeah, I think we have some results for the vision transformers. Yeah.
Yes, and vision transformers can also work really nicely here, as we also we didn't use this in now our comparison because we trained the FisionNet V2 models, but in this case you can see that vision transformers with like some larger vision transformers with even 384 image size only here can go to something like 0887 in this case. But if you look at the training time, I think it was quite significantly. That's even quick, 3 minutes. Yeah, so vision transformers can perform well, and they are usually the most diverse ones to convolution-based models because efficient nets are convolution-based, ResNets are convolution-based, and transformer-based are maybe the most diverse ones in terms of backbone. So I would also always, if you have time, encourage to try some vision transformers and play with them. I think VIT is specifically straightforward to tune. Swin is another kind of a backbone family that you can tune. Yeah, so this is the vision transformer inference prediction, right?
Yeah, and it achieves like 887 on this test data set, right? So it is better than both our models.
So now you could even blend it in, and it should be.
Yeah, and it is again iterative process.
Yes. But also maybe one more thing for the ensembling is really at some point sometimes you need to start tuning models not for the individual performance but for the ensemble performance. So there might be models that are worse individually but really blend better and ensemble better. So it's always good to have on the side just a script with like your current best blend and then check if the new model maybe even helps a lot to the blend. So personally, we usually try to start ensembling and blending earlier because this can be important for some competitions to really optimize the ensemble performance versus single model performance.
All right, and yeah, that is it for our session today. Thank you, and we will go now for the question session, and we also have some questions in Slido already, so we can start with them, I guess. And maybe there will be some questions from the audience. Okay, so the first question is, what do I need to do to team up with Psi? I guess, Philip, it is for you.
That's a good question. I don't know. Be nice to me. I don't know. Usually at this stage we are more teaming up with people who we know, right? Because it's a little bit about not taking risks. But in general, we are always happy to talk to people, and maybe there is a chance at some point. But there's no specific thing I could name that needs to be done.
All right, let's go to the next one. The next one is, which is the best CV model? Yeah, I guess it really depends on their firstly the data set you have at hand, and also for your like preferences. So I'm personally a fan of ResNet architectures. Philip is a fan of EfficientNet. So for me, the answer would be like ResNet is their best CV model. And Philip, for you?
EfficientNet, of course. Yeah,
So-
but it's always, as I said, it's a bit of a personal preference, and this is the nice thing. I don't think there is like a single backbone to rule them all, right? So you can get to the goal with different backbones, and we even saw it here. And the nice thing is to really try and get familiar with different backbones, because it's a little bit about the experience. I have a very good feeling already, because I trained so many efficient nets in my life, to really understand already and have a good feeling of what to try next. And I'm looking at the learning rate and batch size and training loss and so on, and have a good feeling of what to try next. And this is a little bit different across the backbones, but in general, I don't think there is one really that stands out. I still think like ResNet-like architectures, efficient-net like architectures, and width-like architectures are kind of already give you a lot of good results.
Okay, good.
I can also take the next, no warm-up. Yeah, I mean, as we said in the beginning, for this exercise now, we decided to not go with warm-up, but it is something you can tune. Usually what we do is just have one epoch warm-up and then do the decay. This can be better, but doesn't need to be better. It's again, there is no strict answer to what works and what doesn't work. It's always something you need to try. And maybe this is to me the quintessence in machine learning. It's an experimental science. And as soon as you have your setup ready, you can just try whatever feels good, right? If you want to try warm-up, implement warm-up and try it out. Is it better? Good. If not, well, you have it for the next time to try it because you implemented it already. So this is really, I think, what needs to be done.
And I guess we had two similar questions here. And maybe one note for me is that, like, from my personal experience, that for their computer vision models, warm-up is not really useful. So usually, like, just starting with this like largest learning rate is enough. But for their NLP and for the transformers architectures, sometimes warm-up is useful. So even if you're training like only for two, 3 epochs in NLP, still you might want to make one warm-up epoch beforehand, and it usually helps. All right, so now the question is what I need to do
Maybe
to
it works
team up.
better.
Yeah, so to team up with me, I don't know. So for me, I'm not that active on Kaggle, right? So I don't have a lot of competitions. So I'm usually doing like 2 competitions per year. So it should be a good timing. So if there's a good timing, just like send me a message, and if there's interesting competition, let's go for it. So this is easy. All right. The next question: do you use H2 Hydrogen Torch to participate in Kaggle competitions and win with it? Who wants to take it?
I can take this. I mean, in general, Hydrogen Torch is for us rather a place where we really implement whatever we learn on Kaggle and make it available to our customers and people who are using our tools. So it's rather the other way around. So what we find interesting on Kaggle, so we see a new technique, we see a new augmentation working, we see a new setting that we can use. We go ahead, open an issue in our work environment, and we implement it and make it available. So it's rather the other way around. But here, as you can see, for also like training this iterative process, and it's very nice for us also now to use this for teaching purposes and for educational content.
Yeah, let's take one more question because we want to make sure everyone has time for lunch.
All right, sure. So let's just go. This one got the most upvotes, so let's go for it. What can we do if the image size are very consistent and not squared? Yes, this is a nice question, right? Because usually across the datasets, you can see that the images are not the same size. And on Kaggle competition, sometimes the images are of the same size, already resized to the same aspect ratio. And in this particular case, we are usually just like using resize augmentations, and it works pretty well. So because it is also an additional augmentation, like you're augmenting their aspect ratios, and just using their squared images is enough. But there are also like some specific augmentations, like random resized crop, I guess it is called, in Augmentations library, that firstly crops some region of this image and then resizes it to their like specified input of the model. So sometimes you might go to this kind of random crops augmentations as well. All right, there is one. Can we take the last one?
Okay. Yep.
Thanks. What do I need to do to be hired at H2O? Yeah, there is no strict rule, right? So like we have in our team both Kaggle grandmasters and just usual data scientists who are not that active or like have high results on Kaggle. So basically, again, it depends on your like profile and on the goals we need at the moment. So basically, there is no requirement that you need to be a Kaggle grandmaster. So it is not true.
All right, this was awesome. I personally learned a lot, and thanks so much for the speakers. Let's give them a round of applause. Yeah, amazing, amazing session. Thank you so much.